All right, today we're going to learn a new language. And no, it's not Spanish or Mandarin, it's the language of movement itself. We are diving into the secret language of flow, decoding how everything from the air we breathe to the water in our oceans actually moves. I want you to picture a hurricane. From space, we see this huge, swirling, almost majestic structure. But what's really going on down at the level of a single, tiny water droplet? Seriously, how do you even start to describe the motion of a billion of those droplets all moving at once? That question, that's the core challenge of fluid kinematics.
So, first up, a world in motion. See, before we can even get to why a fluid is moving, we have to have a language to talk about how it's moving.
And that's what fluid kinematics is, precisely. It's the study of the geometry of flow. You can think of it like being a detective showing up at a crime scene. You're not worried about the motive, the why, not yet. You're just carefully describing what happened. The velocity here, the path something took there, the rotation of an object. It is all about description.
This brings us to a really fundamental choice. There are basically two very different ways to see flow. You have to pick a point of view to even begin to solve the problem. And here's the huge roadblock. A fluid is made of just countless particles. I mean, you can track a few billiard balls on a table, sure, but trying to follow every single water molecule in a river, it's basically impossible. So how on earth do we get around that? Well, you choose one of two perspectives. The first one is called the Lagrangian view. This is where you try to follow one single particle on its journey. The second view, and this is the one that's way more common in engineering, is called the Eulerian view. Here, you just ignore the individual particles, and instead you plant yourself at one fixed spot and just measure whatever flows past you. Here's a super simple way to picture it. Imagine you're floating down a river in a raft, just moving with the water. That's the Lagrangian view. You're following the flow. Now imagine you're standing on the riverbank, and you dip a thermometer into the water at one fixed spot to see how the temperature changes as the river rushes by. That's the Eulerian view. And almost all engineering work, from weather stations to wind tunnels, uses this Eulerian approach. It's just more practical. Okay, so if we're going to be watching flow from fixed points, how do we visualize the invisible? We need some tools to actually see the entire pattern all at once. Our first tool is called the streamline. The best way to think about this is as an instantaneous snapshot of the flow. Imagine you could just freeze time for a second and ask every single fluid particle, hey, which way are you pointing right now? If you connect all those little arrows, you get streamlines. They show you the direction of the entire flow field, but only for a single moment in time. Then you've got the path line. And this is totally different because it's all about following just one particle, but over a period of time. So forget the snapshot. This is more like a time-lapse photo of a single dancer moving across a stage. The line they trace out is their personal history, their own unique path. That's a path line. And finally, there's the streak line, which is probably the one you're most familiar with, because it's what you usually see in experiments. You know, when you see smoke coming off a wand in a wind tunnel? That line of smoke is a streak line. It's not one particle's path. It's a line connecting all the different particles that have passed through that one single point, where the smoke is being released. Now here's where it gets really interesting. In a very simple, steady flow, that is, a flow where nothing is changing over time, all three of these lines, streamlines, pathlines, and streaklines, are all exactly the same. They're identical. The particle's path is the flow direction, which is the line of Dye. Easy enough. Right, but what about more complex, unsteady flows? What happens then? Take the famous Kármán vortex street, that beautiful swirling pattern you see in the wake of a cylinder. In a flow like that, things get way more interesting, and those three lines can look dramatically different from each other.
And here is the absolute key insight. A streak line has a memory. That smoke trail showing those cool vortices, the pattern you're seeing way downstream is actually a remnant. It's a ghost of what happened upstream a few moments ago. In fact, if you put a velocity sensor right there in that downstream smoke, you might find that the flow is perfectly smooth. The streak line is showing you history, not the present, which is why you absolutely have to understand the difference.
All right, next section. Let's talk about the character of the flow.
It's not just about where the fluid is going, but what is it doing as it goes? Is it spinning? Is it stretching?
So let me ask you a kind of tricky question. If you see fluid particles moving in a perfect circle, does that automatically mean that the flow is rotational? You might think so, but the answer is actually no.
The absolute best analogy for this is an amusement park. Think about a merry-go-round. As you go around the center, your body is also spinning to stay facing inwards. That is rotational flow. Now, think about a Ferris wheel. Your cart moves in this huge circle, right? But you stay upright the whole time. You're not spinning at all. That is irrotational flow. See? The path is circular in both cases, but what the particle itself is doing is totally different.
And the scientific term for this local spinning is called vorticity. A fluid particle on that merry-go-round has vorticity. A particle on the Ferris wheel has zero vorticity. It's the property that tells us if the tiny particles themselves are actually rotating, not just whether their path is circular.
So finally, let's get to the engineer's master tool. How do we take all of this descriptive theory and actually make it useful for building things?
So check out this cool little paradox. In a steady flow, like water coming out of a garden hose, the velocity at any one fixed point, say right at the tip of the nozzle, never changes. But think about a single particle of water. It definitely speeds up as it gets squeezed through that narrow nozzle. So how can it accelerate in a steady flow? Well, this is called advective acceleration. The particle accelerates not because the flow itself is changing, but because the particle is moving to a new location where the flow is just naturally faster.
The mathematical tool that lets us deal with this paradox is called the material derivative. Think of it as a special calculator that gives you the total change a particle is experiencing. It's so clever because it combines two things at once: any change happening at its current location, plus that advective change it gets just from moving to a new spot. It perfectly bridges the fixed Eulerian world with the moving Lagrangian experience of the particle.
So how does this help us analyze something real, like a jet engine? This is where the mighty Reynolds transport theorem, the RTT, comes into play. You see, fundamental laws of physics, like mass is conserved, are written for a fixed blob of stuff, a system. But in an engine, new air is always flowing in and exhaust is flowing out. The RTT is like a magic translator. It takes that pure physics law and converts it into a practical equation you can actually use for a fixed space, like our engine. It is the essential bridge from pure physics to real-world engineering. So if there's one thing to take away from all this, it's that the language of flow is incredibly rich and detailed. It's not just about asking where is it going. It's about understanding its full character, how it tumbles, how it stretches, and how it shears along its journey.
You know, this language of kinematics is what lets engineers understand everything from the lift on an airplane wing to blood flow in our arteries. And that really leaves us with a final thought. If these are the tools we've developed to decipher the incredibly complex motion of fluids, what other complex systems out there, in nature or in technology, could we finally begin to understand if we just applied a similar descriptive language?